Hi everyone, welcome to TitanClass. On this episode of TitanClass, we've got a whole bunch of functions we want to talk about. Part 1, function mapping diagrams. Part 2, function ordered pairs and function graphs. Part 3, a little bit of domain and range. Part 4 will be notation. And Part 5 is slope, average rate of change. Let's try some. Part 1, function mapping diagrams. A mapping diagram is really just two ovals or two circles, right? So what we have here is we're going to have two ovals. Now, they're filled with numbers or objects or letters or whatever we want to talk about. For this particular video, though, I want to focus on just numbers. So the left-hand side oval is going to be our x values, our domain values. And our right-hand oval is going to be our y values, which is our range values. Now, what is the importance of ovals? Well, a function mapping diagram is literally that. It maps our x values to our y values. So let's try a couple. Let's keep it simple. What if I had the numbers 1, 2, and 3 for our x values? Those are our domain values. And let's just say we had a 4, a 5, and a 6 on our range values. Well, these are really ordered pairs on the coordinate graph. But what if I make some arrows going from one side to the other? That means that the 1 is going to pertain to the 4. So one of the ordered pairs in this mapping diagram is 1, 4, x, y. Another set would be 2 to 5. And our final set will be 3 to 6. Remember, xy, xy, xy. Our domain values here are going to be 1, 2, and 3. And our range values here are 4, 5, and 6. Now, is this all that a mapping diagram can give us? No, of course not. When we talk about a mapping diagram, the mapping diagram will also tell us whether these ordered pairs or whether its inputs is a function. Well, let's take a look. Because only one line is coming from the 1, one line is coming from the 2, and one line is coming from the 3, that means that this is going to be a 1-to-1, which is a function. So, what happens if it's not a function? Okay, now in this example, let's say we have 10, 20, and 30. And let's just say we have 1, 2, and 3. What happens if the 10 goes to all three of these values? This would not be a function, okay? Because the x value cannot repeat, meaning an arrow cannot come from the same number and go to multiple numbers or even two numbers. This instance would be an example of not a function, right? What if we just erased this 10 going to the 3 and we made a 20 go to a 3? Would that change this thing? No, it's still not a function. Because again, this 10 cannot have two arrows going to any types of y values. So the 10 is being shared, kind of, to the 1 and the 2. That can't happen. So again, not a function. Let's try a couple examples to see if we really get it. All right, check out this example. Is this a function or is it not a function? Well, you can really just tell by how many arrows are coming from the x values. You see that -3? There are two lines or two arrows coming from there. The -4 only has one and the -5 has one, but that's irrelevant. Because that -3 has two things coming from it, this is not a function. So you would say not a function for this particular set of mapping. Now, it still does have a domain, and the domain is -3. It would be twice though, -4 and -5. The range for this one would just be 6, 7, and 8, right? Let's try one more. What about this one? Is this a function? And the answer is yes, it is a function. But why, do you ask? I know. It doesn't matter if they all go to the y, that's the same y value. It doesn't matter that a 4 goes to a 1, an 8 goes to a 1, and a 12 goes to a 1. Doesn't matter at all. It's the x values that can't repeat. Y can repeat, but the x values cannot. So this would be a function. Let's move on. Okay, for part 2 of this video, let's talk about function ordered pairs and graphs. Let's talk about the ordered pairs first. So let's say that I gave you a couple of different ordered pairs. Let's say 0, 1, 3, 3, 7, 6, and -1, 5. Now, let's take a look at these ordered pairs. The question is going to be something like this. Do these ordered pairs together represent a function? Now, you might see a little squiggly here and here saying that these ordered pairs are members of the same set, which is fine. But let's just say, for argument's sake, that they all form or they all are in the same line. Is this a function? Now again, just like in our mapping diagram problem, we want to identify the x values because they are far more important than the y's when we talk about functions. Do the x values repeat? Meaning, is there more than one of the same x value? Let's see. 0 is an x value, okay? 3 is an x value. 7 is an x value. And -1 is an x value. Are any of these duplicates? And the answer is no, it isn't a duplicate, which means that yes, this is a function, okay? And that's good. Now, we can go one more step, and we can say that 0, 3, 7, and -1 is the domain of this particular set, which means that the range values, or the y values, would be 1, 3, 6, and 5. Pretty simple. Let's try one more to make sure we get it. So when we talk about our ordered pairs, let's say we have 3, 7, 8, 7, 7, 3, and 8, 5. And again, we can say that they're part of the same set. No worries there. Would this be a function or not? Let's take a look at our x values. 3, 8, 7, 8. No. Because the 8 repeats, we can't have two of the same x value. So let's put it into perspective. Our domain values, or our x values, are 3, 8, 7, but 8 again. That means we cannot have a function. So this is not a function because the x values repeat. But let's go ahead and finish this off in terms of domain and range. So the domain is just 3, 8, and 7 because we don't like to write the repeat. And the range value is going to be 7, 3, and 5. We don't have to write that 7 twice. Now, if you wanted to, that's probably fine. But in mathematical, algebraic terms, it's a duplicate. We don't have to write that. But the key of this is it's not a function. Let's move on to see if we can get some graphs here. OK, when we talk about graphs and wondering if they're functions or not, there's a couple things we can look at. First, we can look at something called the vertical line test. Now, that's actually a really super easy test. It basically says if you have a vertical line, you can use your pencil, pen, or in this case, my marker. If you are able to put the marker over top of the graph and the marker only touches it at one point, it is a function. Or we can see if it duplicates upon itself, meaning does the line or graph have kind of like layers? Like if you were going up in an elevator, would you go past the same thing twice? Let's see what I mean. So I'm going to put up 6 graphs here. What'd you say, Titan? That's a garbage graph? Bro, you're a dog. You couldn't draw that any better than me. My dog, Titan. He's spiteful. He didn't get as much dinner as he may have wanted tonight. That's okay. Okay, so here I've got 6 graphs. We have to determine whether they are functions or not. So let's identify with the vertical line test. Let's take our graph number 1 over here. The vertical line test is if I put a pen, pencil, or in this case again, a marker, over top of the graph I drew. Does it touch only once? And the answer is yes, it does. Or if it makes it easier to draw a dashed line, I can draw a couple dashed lines. And if that dashed line only touches this graph at one point, that means it is a function. So for this particular graph, our first one, yes, it is a function. Because again, our x values can't repeat. The vertical line test works in unison with that concept. The vertical line test sees or shows how many times it crosses or how many x's you see. Well, in this particular case, there's only one x for every line that goes down. So we're good. Let's take a graph number 2, the circle. Circles aren't functions. They never will be, nor will they ever have been. They never will be, nor have they ever been. So how do we know it? Well, we know because it's a circle. There's a top and a bottom going through the same exact vertical line. In this case, that vertical line we can use as the y-axis. It touches twice, which cannot happen, which means there's an x value that goes up to this value, and there's another x value that goes down to that value. That can't happen. Now, if you want to use the vertical line test, take a look at what happens when I put my marker over top of the right side of this graph. It touches twice, or it goes through the circle at 2 points. Here is a dashed line that represents my marker. It touches here and here. That can't happen. This is not a function. What about this graph? It's probably drawn really bad. I'm sorry. This is a function because it passes the vertical line test in every instance, meaning I can put my marker over top of it and it would only touch or cross at 1 point. What about this line? Well, this is pretty much a function, we know, because it doesn't ever even squiggly. This triangle, not a function. It fails the vertical line test. I can't put my marker on any part of this without it crossing twice. And this squiggly line, definitely not a function. It crosses a bunch of times if I make a vertical line. 1, 2, 3. That's no good, right? So here we can use the vertical line test, or we can do an eyeball test and see, well, if it duplicates on itself or it has multiple layers, circle has multiple layers, this squiggly has multiple layers on top of itself, and this triangle has the same. No good. Let's move on to something else. Domain and range. Pretty simple concept. We touched upon it earlier, so I'll make this section short. When we talk about domain and range, we know that domain values are x values. We can also call them inputs, though. Range values, on the other hand, are exactly the opposite. Y values or outputs. Now, when we talk about whether something's a function or not, that's kind of irrelevant when we ask what the domain values are or what the range values are. It doesn't have to be a function to still have domain and range values. Domain and range values don't just disappear because it's not a function. Let's do one to see what we're talking about. Let's say I have a ordered pair set of 0, 4, 3, 3, and 3, 7. And we'll say it's part of the same exact set. This is not a function because the 3 repeats. I can't have 2 of the same x value. But there's still a domain and there is still a range. Remember, domain values are x. So we've got a 0, a 3, and another 3. But again, we don't have to write that second 3 because we don't like to write duplicates. These are my domain values. My range values, though, are the y values. 4, 3, and 7. So there you have it. Our domain values are x, but again, because this was a duplicate, we don't need it. And the range values are y. No duplicates there, but again, it doesn't matter. Y can repeat. It's the x values that make this not a function. Okay? Pretty cool. Let's keep going. What's the domain and range of this ordered pair set? I'll wait. If you told me the domain was 7, 8, -3, and 0, and that the range was -3, 9, 4, and 0, you're looking good. The domain values are simply just the x values, or the numbers in the front of each ordered pair, and the range values are the back values, or the y values of each ordered pair. Let's move on. Okay, function notation. Well, that's a fancy phrase for y. Not like why is this the way it is? Just y, the letter. Function notation is f of x, meaning f of x. That's how we say that. Well, f of x, again, is just a really fancy way for us to say y. F of x is y. It's just a better way to write it when we talk about these algebraic properties that we're going to. Why do we do that, though? Well, it's complicated. For now, we'll keep it simple. So when we have function notation, which again, this is what function notation is, we have a better way of identifying different types of graphs or different types of functions on the coordinate plane. Now, in terms of this video, we use function notation to find outputs when we are given inputs. And remember, outputs are y values, inputs are x values. So let's try a couple of examples. Let's see if we can figure out these 3 problems. Now, we need an equation. So let's do one. Let's say we have an equation, f of x equals -2x plus 7. That is my equation. The function of x equals negative 2x plus 7, or y equals negative 2x plus 7. They say the exact same thing. But when we use this notation, function notation, it helps us identify what the input is, or a specific input, in the cases here you say, to find a very specific output. So this top equation, or the top notation here, does that a lot better than this bottom one does. So here's what we're going to do. We're going to take this equation, we're going to replace that x and that one with 3. And every time we replace the x value, we're going to put parentheses around it. And then we're going to solve. The function's value when x is 3 is going to equal negative 2 times 3, which is negative 6, plus 7, meaning the function's value when x is 3 is going to equal 1. Now, what does that actually mean? That means the ordered pair is a spam risk, calling my phone and my iMac and my Mac. Get it, Titan? I'm teaching. 3, 1. That was really bad timing. That's never happened before. Consider yourself lucky. So my ordered pair is 3, 1, meaning when the input is 3, the output is, Titan's not pleased. When the input is 3, the output is 1. Go ahead and try the other 2 on your own. I'll wait. Okay, so if you got f of 8 equals negative 9 for our first one, and f of 7 equals negative 7 on your second one, you're looking amazing right now. So what did we do? I took that 8 for x equals 8, and I plugged it into both x values of the function. I simplified and solved. So I got negative 9 when the input was 8, meaning my domain value is 8 and my range value is negative 9. Here in the pink marker, which actually kind of sucks compared to the yellow. The yellow really pops, but there's only 4 colors, and I didn't like the green against the yellow because it didn't really clash very well. So when I put in 7 for my x value and plugged it in here, I simplified it and got negative 7. Let's move on. Okay, our last part of the video today is slope and AROC. AROC stands for average rate of change, which is what slope is, but average is really a misleading term. So let's talk about what this means. Slope is what we call a rate of change. Now, slope is what we call a constant rate of change. But we don't like the acronym CROC, because that sounds crappy. So we just say rate of change. The term average rate of change, or AROC, really kind of talks about when I'm trying to find 2 points that are not on a straight line. Meaning, if we have a curved line, and I wanted to find the slope, or the average rate of change from here to here. That means I'm actually finding the straight line distance from the first point to the second. Now, this is for average rate of change. Now, on rate of change, our lines will always be straight, right? Because the rate of change from this point to this point is exactly the same as from this point to this point. That's why it's called constant, because it's the exact same distance or same slope every time. Here, however, it won't be the same if I choose a different set of points. For example, if I start from here but I want to stop here, take a look at that straight line. That's way different than that. That's why we call this an average, because it depends on the lines, or it depends on the points. But this one, the slope's always going to be the same. So we're really going to focus on just finding slope in general. To find slope, we need a formula. And there's actually a really good one. The slope formula is y2 minus y1 over x2 minus x1. Now, what does that really mean? Well, let me demonstrate with an example. Let's say we have the points negative 2, 3, and 4, 4. I want to find the slope between these 2 sets of points. I need 2 points, or 2 sets of ordered pairs, to find slope. And here we go. I need to label these points. That negative 2 is an x value. But it's the first x value that I see from left to right, or it's the first x value that I read from left to right. 3 is a y value. It's the first y value I see. 4 is another x value, but the first 4, but it's the second x value in order that I saw. That's why we label them this way. And then y2 is the second y value that I see. So we're reading it left to right, like a book. So we have to label it as such. Now, let's plug in our numbers and see what we get. I'm looking for the y2 value first. Well, the y2 value is this 4. Then I draw the minus sign. The minus sign is built into the formula. I can't ignore it. y1 is 3. Divided by x2, which is also 4. The minus sign is built in. I can't ignore it. I have to write it. Now, it just so happens that this is a negative 2. I have to write that negative 2. That negative, which I wrote here, is not that negative 2. That negative is built into the formula. I have to write it, which is actually very helpful. And I know mathematicians and algebra people and all kinds of math teachers will say, don't double sign, it's so bad in math. That's actually not true. It's really helpful here because it tells you or hints that this is going to turn into a positive, which is exactly right. So let's go ahead and work this out. 4 minus 3 is 1, and 2 negatives make a positive. So it's going to be 1 over 6. Do not give your teacher a decimal. They don't want that. This is the answer, and that is the slope. So let's move on. So we just did an example with 2 sets of points. But what happens if it's written in function notation? So let's say we have g of 4 equals 10, and we have g of 12 equals negative 6. How would I find the slope of those two things? Well, remember that function notation is x in the parentheses, which equals a y value. X in the parentheses, which will equal a y value. This 4 is x1. Again, it's the first x value that I see left to right. This 10 is a y value. It's the first y value that I see from left to right, which means this 12 is x2, and this negative 6 is y2. Let's plug it in and see what we get. y2 is negative 6, minus sign. y1 is 10, over x2 is 12, minus sign built in, x1 is 4. Now you can use a calculator, but I'm a math person. I'm going to do this in my head. Negative 6 minus 10 is negative 16. 12 minus 4 is 8. We always have to simplify in mathematics, especially with slope. So negative 16 divided by 8 will simplify to negative 2 over 1, or just negative 2. So the slope, or average rate of change, on these 2 points is negative 2. Let's finish up. Okay, things to remember about this video. Number 1, use a calculator. You don't want to get hung up on the arithmetic part of this, meaning the addition or subtraction with the negative numbers or whatever. If you use a calculator, it's going to keep your mind on the big ideas. Slope, AROC, function notation, and really understanding whether it's a function or not. Right? Use that calculator because you can't really afford to make silly mistakes on things that you should know. Number 2, simplify, especially with slope. You've got to make sure you always simplify your fractions. And I'm not talking about decimals, because decimals are a no-no when it comes to graphing. Decimals are really, really difficult to graph. Keep it as a fraction and make sure that if it's a negative, it stays a negative. And then finally, take your time. You don't want to rush through things when it comes to slope, and certainly not with functions. These problems don't have a lot of layers to them, so you want to make sure you focus on the one layer at hand so you can get a fantastic grade, a fantastic score, and move it along. See you next time.